All right, we're on our additional focus area 2 about wave properties. This focus area has 4 objectives, all of which are pretty short, so we'll knock this out pretty quickly for you. It's going to tie into what we learned on wave basics, our power focus area. So some things we really need to keep in mind are mechanical waves. Remember, waves that require a medium, something to travel through like air or water, things like that were our most common examples. Those kind of waves are created by vibrating particles. And these vibrations pass on to particles that are nearby and hit them. And then they start to vibrate and they hit nearby particles and those vibrate. And the next one, the next one. And eventually they hit your eardrum and that's how you hear it, which is kind of what you see in this picture. The picture is of a guitar string being vibrated. And what happens when this is plucked, it shakes back and forth. And that hits the air molecules and starts them vibrating back and forth. And then it hits more air molecules and more and more and more. And eventually those hit your ear, and that's how you're able to hear. Remember, electromagnetic waves were a little different. Electromagnetic waves like light and X-rays and radio waves, they don't need a medium, but they can act like a wave. And they can also act like a particle. Now, we're not going to focus on the particles here, but acting like a wave is why we mentioned the electromagnetic waves as well. EM waves are longitudinal, if you remember, like we see in the picture here. And some of our key terms, amplitude, we said was the distance between this middle point, which is called the resting point, and the height of it, called the crest. Again, the crest is the top, the trough is the bottom. And the wavelength was the difference between one crest and the next, or one trough in the next. This is the important, well, not that the other wasn't important, but this is the important new stuff that we don't know much about. The speed at which sound waves travel, it really depends on the medium it travels through. And when we say that, it's really talking about how close are those molecules in the medium packed. If you look down here, gas molecules are spread apart. You can see they're further apart than the liquid molecules in the middle, and the solid on the right are the closest together. These right here, it says solids are fastest, but the reason they're fastest, when sound waves hit a molecule in the solid, they vibrate that molecule, and then there's another molecule right there. It's just less time because the distance between the molecules is so close. So believe it or not, and please, please, please don't try this, but if you were to put your ear on a train track and the other ear is in the air, you would actually hear the train first through the rail and then a split second later through the air, because the sound wave of the train would pass quicker through that solid metal that your ear was on than the gas of the air. And another big factor that affects the speed of waves, like sound waves, is temperature. If you remember, we said temperature is just measuring how fast molecules move. The faster they move, the more increased the temperature is, or the hotter it is. So when temperatures are warmer, like in the air, sound actually travels quicker, and it's all about those molecules. If the molecules are moving quicker, when they get vibrated by the sound wave, they're going to hit another and another and another molecule and get that moving quicker to your ear. And that's it for this new objective.